let's start with the Bernoulli and the uniform. So those are the easy cases. So the Bernoulli or binary, okay, slash binary. So the binary random variable, so x is equal to, the possible values are 0 or 1, and the probabilities are 1 minus p and p. So the expected value of x, you multiply 0 times 1 minus p, 0 times 1 minus p, plus 1 times p, which is equal to, so you remember, it's the formula, it's just a formula. Okay, so this is p. Okay, very simple. Okay, so if the success probability for your Bernoulli or binomial binary random variable is p, okay, then the expected value, so I'll box it temporarily, expected value of Bernoulli with success probability p is just p. Okay, so if you flipped a coin, if you flipped a bias coin with probability p of heads, okay, and you gave a 1 for each heads and a 0 for each tails, then on average your score would be p. Okay, the uniform. So the uniform random variable. So this is just an exercise in computing the expected value. Once we identify the random variable and its PDF, we just compute the expected value. So our random variable, let's suppose it can take on the values 1 to n. Okay, so 1, 2, 3, 4, up to n. Now this is not something you want to memorize, because sometimes you might have a uniform random variable, on 0 to n, or sometimes you might have a uniform random variable which could take the values 5, 9, and 13. Uniform just means each of those possible values is equally likely. So here I have its PDF. Since it's uniform, it must be 1 over n, 1 over n, 1 over n, 1 over n, dot, 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 1 over n. Why 1 over n? Okay. So pause the video. Think about it for a couple of seconds. 1, 2, 3, 4, 5. Okay, now if you're coming back and you're saying, just tell me why 1 over n. Okay. Well, or if you said, since all of them are equal and they must add up to 1, they must each equal 1 over n. So that's why 1 over n. So we know, okay, that, these are all the possible values of x, so the sum of their probabilities must be 1. Okay, but now the expected value of x is just equal to, you multiply the possible values by their probabilities and add. So 1 times 1 over n, 1 times 1 over n, plus 2 times 1 over n, plus 3 times 1 over n, plus up to n times 1 over n. So let's factor out the 1 over n. It's 1 over n times 1 plus 2 plus 1 over n times 1 plus 2 plus 3 up to n. Up to n. Okay, and this sum we know. If we wanted to be fancy, we would say, showing off our fanciness. This is 1 over n times the sum from I equals 1 to n of I. And we know this sum. This is a common sum. It's 1/2 n, n plus 1. And so the result is 1 over n times 1/2 n, n plus 1. So the 1 over n's cancel. And so this is n plus 1 over 2. Okay, so the average of a uniform random variable which takes on the values 1 to n, the expected value is n plus 1 over 2. Okay, and you could compute this sum and the average, the expected value for any uniform random variable. It amounts to computing a sum. And what we see here, and even in the definition, is computing expected values means we need to be good at computing sums. Okay, so that's another benefit of having tackled sums, some chapters ago. Okay, so let's erase and then do the other two big ticket random variables, the binomial and the expected waiting time. Those are going to be tough. Okay, those sums are not going to be easy to do, but we have some tricks up our sleeve. I'll show you them.